Hello, and welcome back to Shiksha DaCosta. Today we're going to interpret some sinusoidal graphs. This is part of our unit on connecting the graphs, the equations, and the actual real-life applications of sine functions. As part of this lesson, you're going to learn what the connection is between a real-world situation and its related sinusoidal graph. And you're going to be able to do that by making connections, by doing an investigation with technology, between changing a real-world situation, especially one that can be modeled by a periodic function, and watching how does the corresponding graph transform or change. To start off, take a look at these two diagrams. Here we have two arms that are rotating around a center, and they're rotating at 1 degree per second, but obviously it doesn't look like that. In this case, just pretend that the video is sped up. And what if we wanted to graph the y value of this point after x seconds? What do you think that graph might look like? Well, hopefully you've done an investigation already and you recognize what the graph of sine of x looks like. So a wheel that has a radius of 1 rotating after x seconds. To find that out, we just have to imagine that right triangle. So imagine that the wheel has rotated about this much. Here's the arm. We can create a right triangle out of that. And if we want to find the y value, we're basically finding how high is the point above the x-axis, as long as this has a radius of 1. And if we want to find out, if this is x degrees, and we want to find out this side length, this is the opposite side, we know the hypotenuse. And so we would use the sine ratio in a triangle like this. Sine of this angle should give us the opposite divided by the hypotenuse. Now, if we want to find out exactly what's the y value, well, y divided by 1 is just y. So it looks like all we have to do to find the y value is take sine of x. Now notice that in this case, we already know what this graph looks like. Looks kind of like that. So here we see the function f of x equals sine of x. But what if that wheel was bigger? In this case, check out this wheel. This has a radius of 2 units instead of a radius of 1. In this case, how would we find out the height of the point or the y value of the point after it rotates? I'm going to make a very similar diagram to this one right here. So this is what my diagram might look like. And in this diagram, again, I have a right triangle, very similar, except my hypotenuse is 2 meters. See if you can figure out how you could calculate the y value after a rotation of x degrees. Pause the video here and try to do that. Well, hopefully you recognize that, well, this is the same situation that we've got here. Sine of x equals y over 2. But there is one small difference, that this is divided by 2. So we can't just say y divided by 1 is y. We actually have to isolate y. And to do that, we just multiply both sides by 2. Multiplication is the opposite of division. And when we cancel those out and do the same thing to the other side, we find out that to find the value of y, we have to take sine of the angle and then multiply that number by 2. Now, the graph of this is tough to imagine if you have no experience with it. But go ahead and use some graphing software to graph this and take a look at what you notice. Hopefully you saw that the graph kind of looks like this. Did you notice anything when you compared this graph to the original graph f of x equals sine x? Well, in this case, the y value of that point, after a 90-degree rotation, you can see it should be up here. And that is actually 2 units above the x-axis, not 1 like it was here. It's twice the height. And in this case, the only difference between these two graphs seems to be the amplitude. And that's one thing to take away from this investigation, that the radius of the wheel, as that gets bigger, that controls the amplitude. Well, what if that arm was rotating at 3 degrees per second instead? That's triple the speed of the last time. If we were to try to find the y value of the point after x seconds, what would that graph look like? To find this out, I'm going to ask you to copy and complete this table. So pause the video, copy down this table. Here you've got a bunch of times. Find out what the angle would be and exactly what the y value of that point would be. Well, hopefully you saw that if the time is 0, the angle is still 0, and that would look like just like that, with the y value of the point being 0, because it's still on the x-axis. But once it starts rotating outwards from here, after 30 seconds, the angle would actually be 3 degrees per second, so that's an angle of 90 degrees. And that would mean the point will have rotated until it's all the way here at the top. And its y value would be, as you can see right here, 1. After a minute, the angle would be 3 degrees times 60 is 180 degrees. And that would mean that the point will have rotated all the way around. So that's 30 seconds and now 60 seconds. And that's an angle of 180 degrees. And any point here has a y value of 0. After 90 seconds, the point will have rotated 270 degrees. And that's all the way down here at the bottom. And that would give you a y value of -1. And after 120 degrees, 120 seconds, that would make the angle of rotation a full 360 degrees. So it's right back where it started at 0. Notice that it completed one period a whole lot faster. Instead of taking 360 seconds to complete one period, it completed it in just 120. And because this is a periodic function, I know that, as the angle is always going to increase by 30 seconds, the angle is always going to increase by 90 degrees. The time increases by 30 seconds, so 3 times that every single row. And the y values are just going to repeat this pattern right here. So it's going to be 450 and 1. Then plus 90 is 540 and 0. Plus 90 is 630 and -1. Plus 90 is 720. And now we're right back to repeating this exact same pattern. So hopefully your table looks something like this. I'm just going to break down what was happening in this table and how we can actually come up with the y value directly from finding out the time in seconds. So in this case, the time is the independent variable. That's the only thing that wasn't really changing here. But we found the angle by taking the time and multiplying it by 3. So if the time is x, the angle would be 3 times x. And then we took this number, 3 times x, and we put it into the sine function to find the height of the point, or the y value. And that would look like this, sine of this number, which is 3x. And if you want to take this right now, pause the video and graph y equals sine of 3x and see what you notice. Well, you would see a graph, if you did that, that looks something like this. This is the graph of the same wheel rotating at 3 degrees per second. Notice that it completes one full period in 300 and instead of 360 seconds like the original, it does that in just 120 seconds. And so in 360 seconds, it can actually complete 3 periods, which makes sense because it's moving at triple the speed. In this next part of our investigation, the arm is right back to rotating at 1 degree per second, but now we've actually moved the circle 2 units higher. So where the center of the circle used to be at 0, 0, the origin, now it's at 0 and 2. So the whole circle has moved up. How does that change our table of values? I'll do the first couple of rows for you and see if you can continue on from there. So when the time is 0, remember the point starts over here on this on the right side of the circle. And when 0 seconds have passed, the angle is 0 degrees. And the point itself, its height, its y value is not 0. Now the y value of this point would be 2. After 30 seconds, the angle is 1 degree per second, so it has rotated 30 degrees. And we know that if this was at the origin, the height would be sine 30, which is 0.5. But now, not only is that 0.5 units there, but that is 2 units above the x-axis. So we have to add that 2 units and then add that to the 0.5 that we get from sine 30. That would actually be 2.5 units after a 30-degree rotation, right there. After 60 seconds, and I'll just do one more row here, remember the point is going to move to here. And if I wanted to find this distance just right here, that would be sine of 60 degrees. And that's 0.866. 0.866 plus the 2 from here, from the movement up, gives us 2.866. So if you can, and this one will be quite tough, I think, see if you can finish this tape, copy and complete this table for this investigation. Well, hopefully you saw that after a 90-degree angle, a 90-degree rotation, the point is up here, and that is exactly 3 units above here. So that sine of 90 degrees is 1, plus the 2 units from here gives us 3. After 120 seconds, the angle is 120 degrees, and the height, now it's coming right back down to 2.866. After 150 seconds, the height would be at 2.5, so right over here. After this would be 150 degrees, so right over there. That would be 2, plus this distance, which is 0.5. And then after that, after 180 degrees, it's over here, which is 2 units. Now it's back at the center line of the circle. Now it's going to start its rotation downwards. 210 degrees would give it a height of 1.5. Why 1.5? Well, we know that this distance over here between the center line and right down here would be 0.5. That's sine of 30. So if I'm starting at 2 and I'm going down by 0.5, that would land me at 1.5. Very similarly, 240 degrees would look like that, where this distance is 0.866. So 2 minus 0.866 gives us 1.134. So that right there, and we can even estimate that that looks pretty good, 1.134, that's about there. After a 270-degree rotation, the point is all the way at the bottom. And if it has a radius of 1, that means that the height of the y-coordinate is 1 as well. And now we notice that it's going to, as it comes back up, it's going to repeat these values of 1.134 and 1.5 on its way to its original position at a height or a y value of 2. So this is what your table kind of should look like. Notice how we calculated y. We took the x value, that's our time. That gave us the exact same value as the angle of rotation, because it's 1 degree per second. Excuse me. And now to find y, we had to take sine of this angle. That would only give us the distance from the center, the horizontal center of the circle, which was already moved 2 units up. So we had to add 2 to it. So we took sine of x and we added 2 once we had evaluated that. Go ahead and pause the video and graph this and see what you notice. Well, hopefully you saw that, if the center of the circle was already moved 2 units up, that creates a graph that looked kind of like this. And notice, compared to the original graph of sine x without this plus 2, it's actually 2 units higher, 2 units exactly. We can take all 5 of the key points of the sine function and just move them 2 units up. So 2, 3, 2, 1, 2 is where those key points are now. So what happens when you move a circle up or down? When you move the center of it up or down by a certain number of units, it looks like that changes the midline. The midline used to be at 0. Now it's at 2. And of course, the sine wave moves up and down comparatively to the midline. In this third and final investigation, the arm is still rotating at 1 degree per second, but now it actually starts at a 90-degree rotation from here. So it starts right here. Now, if I wanted to graph the y values after x seconds, what would that graph look like? Copy and complete this table of values, and then we'll take that up. Well, hopefully you recognize that, okay, at 0 seconds, the angle is 90 degrees already. That's where it starts. And if I want to find this distance, sine of 90 is just 1 unit, right? And that's exactly the distance or the y value of the point if it would be right here. After 30 seconds, it has moved, rotated 30 degrees over, and now the angle of rotation is 120. And we can find that that distance is sine of 120, which is 0.866. After 60 seconds, there was a rotation of 60 degrees, but because we started at 90, 90 plus 60 is 150. So the angle is still changing by just 30 degrees every 30 seconds, 1 degree per second. And to find the y value, what do you do? How can you find the y value based on the time? Go ahead and copy and complete this table. Well, hopefully you recognize that that was just sine of whatever the angle is, because it doesn't really matter how much time has passed. The time affects the angle, but the angle is really what tells us the y coordinate of this point. So after 90 seconds, we have rotated a total of 90 degrees from 90 degrees, which is 180. And 180-degree rotation would have left us right over here with a y coordinate of 0. And just like that, I can just find sine of the angle, and that will tell me the y coordinate. And once you've done that, just go ahead and graph the time versus the y value, just like we saw here. And if you want to use a graphing software, let's break this down. We had time, that was our independent variable. To find the angle, we took the time and we added 90 degrees to it. So from 0, we went up by 90 to 90. 30 plus 90 is 120. 60 plus 90 is 150, and so on. And then to find the y coordinate, we just did sine of whatever this number is, x plus 90 degrees. We added 90 first, and then we put all of that into the sine ratio. And if you want to graph this, y equals sine of x plus 90 in brackets, it would look something like this. Excuse me. This is the y coordinate of the point. If it starts at the top after already a 90-degree rotation has been applied. What do you notice about this, especially compared to the original sine wave, sine x? Well, hopefully you notice that the period has shifted slightly. Like it's still the same. The period is still 360 degrees. If I go from here, that would be one complete cycle, 360. But actually, the sine wave starts on the midline, and it starts by increasing. And over here, I can see that that happens over here. This is the midline, and here's where the function starts increasing. So the period starting location is actually negative 90 degrees. Isn't that interesting and weird? It's almost like we took our original sine wave and we moved it to the left by 90 degrees. Some of the things we've noticed in our investigations today are as follows. In a real world situation, the radius of that wheel that is spinning, the speed that it's spinning at, and the height of the center or the axle, those all affect the graph that's created. The radius would tell us the amplitude of the graph, like we saw in that mine's on. The rotation speed will determine the period, like we saw in our first investigation. The height of the axle determines the midline, like we saw in our second investigation. And sine of x usually starts on the midline and it starts by increasing from there. But the starting point of the rotation, if it doesn't start at the right of the circle, if it starts somewhere else, that will determine where the function sine x has moved to the left or right. In this example, Depeche is getting on the Eye of London, which is a cantilevered observation wheel in London. He gets on at the bottom, and the bottom platform is 15 meters above the ground. We're going to create a graph of his height in meters in terms of time, which we're going to measure in minutes. So if he gets on 15 meters above the ground, that would be like him getting on right there. And that height above ground right now is 15 meters right there. That's the bottom. That's the minimum height that he will be while he's on this ride. And he does that 0 minutes, right? That he does that at the very start. That's where he gets on. So at 0, he will be at the minimum, which is 15 meters after 0 minutes. Now, the eye actually has a diameter of 120 meters, so that would be like this distance right here. And we know that the size of the wheel affects the amplitude, but it's not the diameter that does it. It's the radius. And if the diameter is 120 meters, the radius would be half of that, which is 60. And so the amplitude of this graph should be 60. And because the amplitude is the distance between the maximum or the minimum to the midline, I know that if I have the minimum here, the amplitude is 60, and that would tell me that my midline should be right over here. From 15, I went up by 60 to get to 75. And remember, the midline is very closely related. It's actually very, exactly related to the center of the wheel that is rotating, the axle. And so the axle is actually 75 meters above ground in this case, and that creates a midline of y equals 75. We're not done dealing with the amplitude because the amplitude can be used again, actually. This can tell us the maximum is 60 units above this, 60 meters above the midline, which would be here, right? If the midline's at 75, 60 meters higher would be 135. That's the maximum height that Depeche will get to. And that will happen after half a rotation. Now, a complete rotation happens in every 30 minutes. So if he starts here, after 30 minutes, he will go all the way around and he'll end up right back where he started. A quarter of the way through, so if he goes from here up to here, that will take him a quarter of 30 minutes. 30 minutes divided by 4 is 7.5, 7.5. So after 7.5 minutes, his height is the same as the center axle, which is 75 meters. After another quarter, so after half a rotation, which would be every 15 minutes, he would be at the maximum. He would be all the way up here, and that is after half a rotation at 135 meters. Now, after 3/4 of a rotation, he'd be coming right back down to here, the same height as the axle once again, which is 75 meters. And that happens 3/4 of 30 is 3 over 4 times 30 is 22.5. And so after 22.5 minutes, he's going to be right here at 75 meters. And finally, after a full rotation, he will be all the way down here. That will take him a full 30 minutes. And then he'll be right back at the bottom, at the minimum height. And that's 15 meters. Now, he's obviously, this is an observation wheel that goes around again and again and again. So if he doesn't get off at this point, we can connect all of these dots to, get a rough sketch of his height. And then we can actually keep going with this exact same pattern because this is periodic. He's just going to go do this again. And so I can draw that very same sketch again and again. And if I needed those the points to help me graph this, I could take this point and I can add one period 30 minutes later. So from 15 plus 30 is 45. And right there, he's at the maximum again. Plus another 30 is 75. And there he is at the maximum again. And I can do the same thing for the times that he's at the axle's height and at the bottom platform. And by doing all of this, this is the graph I should have been able to sketch out. And this describes his height in terms of time while he's on the Eye of London. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.